Before the light, before the stars, before time itself, what was there? It is one of the oldest questions a human mind can ask. What happened before the beginning? But to ask this earnestly, scientifically, is to tread a dangerous line between logic and illusion. Because in physics, before implies time, a timeline, a sequence, a ticking clock. Yet according to our best understanding of the cosmos, time itself began at the Big Bang. There was no ticking, no before, no elsewhere waiting, only the birth of space-time, not within space, but as space, not after time, but as time. In 1915, Einstein's general theory of relativity transformed our conception of reality. Space and time are not separate entities. They are woven into a single dynamic fabric, space-time, warped by matter, stretched by energy. And in this framework, the Big Bang is not an explosion in space, but the origin of space itself. Everywhere we look, galaxies are receding. The cosmos is expanding, not from a central point, but within itself. And when we rewind the equations, run the clock backward, we do not find a prior universe. We find a boundary, a place where our models collapse. A singularity. Does this boundary represent a true beginning? A creation out of nothing? Or is it merely a limit to our current theories, a wall in the mathematics, behind which reality continues unseen? This episode is not about science fiction. It is about physics at the edge of what we know and the bold attempts to peer beyond that edge. We will explore the frontiers of theory, where time loses meaning, where the universe tunnels into being, and where cosmologists dare to ask, could the Big Bang have been a transition rather than a beginning? Welcome to Anantum and beyond. When we trace the universe backward through expanding galaxies, through the fading afterglow of the Big Bang, we find that all paths converge to a single moment, a singularity, not a point in space, but a point in space-time where the density of matter, energy, and curvature becomes infinite, and the laws of physics as we know them cease to apply. This is the foundation of the classical Big Bang model. In 1922, Russian physicist Alexander Friedmann solved Einstein's field equations under the assumption that the universe was homogeneous and isotropic, the same in every direction, on large scales. His solutions, refined by Georges Lemaitre and later confirmed by observation, showed that a static universe is impossible. The cosmos must be expanding or contracting. The Friedmann equations describe how the scale factor, the size of the universe, evolves with time. In 1929, Edwin Hubble published his groundbreaking discovery. The farther away a galaxy is, the faster it appears to be receding from us. This observation, now encoded in Hubble's law, gave the classical Big Bang model its first solid footing in reality. It told us the universe had a beginning, a moment when the scale factor was zero, and all distances between all points were collapsed into a singular state. But this classical view carries a fatal flaw. As we approach t equals 0, the equations break down. Time becomes undefined, energy density diverges, the curvature of space-time becomes infinite. This is not just a physical barrier, it is a mathematical singularity, a point where general relativity loses predictive power. And in science, when a theory predicts infinities, it's not a sign of deeper truth. It's a sign that the theory has reached its limits. To understand what happened at or before the Big Bang, we must go beyond classical physics. We must enter a realm where gravity and quantum mechanics collide, a domain smaller than a proton, lasting less than a trillionth of a second, the Planck epoch. To understand the beginning of the universe, we must turn to a moment so early, so alien, that all familiar physics breaks apart. The moment is called the Planck time 10 to the power of minus 43 seconds after the Big Bang. At this scale, time becomes granular, distance becomes uncertain, and space itself, the very arena of existence, flickers and foams like a storm on a quantum sea. This is where general relativity fails. Einstein's equations describe space-time as smooth and continuous, but quantum mechanics tells us the opposite. At microscopic scales, nature is ruled by uncertainty. Where is a particle? What is its energy? How does it interact with a field that has no classical geometry? These questions have no single answer. They are governed by probability, a shimmering haze of potential states, not certainties. At the Planck scale, even space-time itself becomes quantized, no longer a stage for physics, but a dynamic actor, subject to the same jittery rules as matter and energy. Physicists call this turbulent chaos quantum foam, a sea of ephemeral particles, black hole fluctuations, and virtual energy fields, blinking in and out of existence in timescales too small to conceive. This is not conjecture. It is the mathematical implication of applying quantum principles to gravitational systems. But here lies the deepest impasse in modern physics. We do not yet have a complete theory of quantum gravity. Several contenders have emerged. String theory proposes that particles are tiny vibrating strings, whose modes of vibration determine mass and force. Loop quantum gravity suggests that space is woven from finite loops, discrete units of area and volume. Causal set theory, emergent spacetime, and even holographic principles attempt to reconstruct reality from information itself. Each approach offers a glimpse beyond the classical wall. But none are complete, none are confirmed, and none yet describe the true nature of time at t equals 0. Still, quantum cosmology allows us to ask new questions. Could the universe have tunneled into existence from nothing? Is time an illusion, an emergent property, not a fundamental one? Could before the Big Bang be hidden in dimensions we have not yet discovered? The deeper we look, the more the boundary of the Big Bang blurs, not into nothingness, but into something stranger than we have ever imagined. What if the universe has no edge? What if time itself, the one thing we assume, must begin simply curved smoothly into existence? In the early 1980s, physicists James Hartle and Stephen Hawking proposed a radical solution to the problem of cosmic origins: the no-boundary proposal. A model in which time does not emerge from a singularity, but from a smooth, finite, boundaryless geometry like the surface of a sphere. Imagine standing at the South Pole. It is the start of the Earth's longitudinal lines, yet it is not an edge. There is no before the South Pole, just curvature and continuation. Hawking argued that the Big Bang could be the same. To describe this, Hawking and Hartley invoked a mathematical tool known as imaginary time. Instead of modeling time as a straight line with a beginning, they rotated it into Euclidean space, where time behaves like a spatial dimension. In this geometry, the early universe resembles a four-dimensional hemisphere, finite in size, but without edges. No singularity, no moment of creation, no before. This model preserves quantum mechanics and general relativity without invoking a singularity. Instead of a beginning, it offers a boundary condition, one in which the laws of physics remain smooth, even at the origin. And yet, it's not without controversy. The no-boundary wave function is notoriously difficult to normalize. Its predictions depend heavily on initial assumptions, and it remains a mathematical proposal, not an empirical description. Still, the elegance of Hawking's vision lies not in finality, but in possibility. A universe that begins without beginning. a cosmos whose earliest moment is not a point, but a process, where time is not born in a bang, but unfolds gradually from the quiet curvature of nothing at all. What if the Big Bang was not the beginning, but simply one chapter in an eternal story? Across cultures and epochs, humans have imagined time as cyclical, not a line with a start and end, but a wheel that turns forever. Modern physics, too, has begun to consider this possibility. Nobel laureate Roger Penrose has proposed one of the boldest cyclic models, conformal cyclic cosmology, or CCC. In this model, the universe expands eternally until it becomes empty, cold, and flat, so stretched that time, temperature, and mass lose all meaning. At that point, a remarkable thing happens. The geometry of that empty future becomes conformally identical to the hot, dense state of the next Big Bang. Time does not stop, it resets. According to Penrose, our Big Bang may be the continuation of a previous universe's infinite future, a cosmic aeon giving birth to the next, with no true beginning or end. Traces of this, he suggests, may survive as subtle patterns in the cosmic microwave background, concentric rings of low-variance temperature fluctuations, like fossils from a past aeon. Controversial, certainly, but not impossible. Another cyclical theory comes from string cosmology, the ekpyrotic universe. In this model, our universe exists on a four-dimensional membrane or brane floating in a higher dimensional space. Every few trillion years, our brane collides with another parallel brane, and that collision ignites a Big Bang. The universe does not emerge from nothing. It emerges from interaction, a cosmic heartbeat set by the physics of extra dimensions. Both of these models, Penrose's CCC and the ekpyrotic universe, offer a powerful alternative to the traditional singular beginning. They suggest a cosmos that renews itself, a universe that may be older than time as we know it. But they also raise profound questions. What survives between cycles? Can information persist from one universe to the next? Is time truly infinite or merely reborn? In these models, the Big Bang is not the origin, but an echo, a threshold through which universes fall again and again, each time carrying with them the silent imprint of all that came before. Can something come from nothing? To the human mind, the idea seems absurd, but in quantum physics, nothing is far stranger than it sounds. The vacuum, what we call empty space, is not truly empty. It is a restless sea of uncertainty, defined by fluctuations in energy, particles, and even geometry. According to quantum field theory, nothing is unstable, and under the right conditions, even a universe could tunnel into being. This is the essence of the model proposed by physicist Alexander Vilenkin in the 1980s, that the universe is the result of a quantum tunneling event from a state of absolute nothingness, not from a pre-existing vacuum, not from a collapsed geometry, but from a condition with no space, no time, no matter, no entropy, and no observers. In quantum mechanics, particles can tunnel through barriers. They have no classical energy to overcome a phenomenon observed in nuclear decay, semiconductors, and fusion in stars. Vilenkin's insight was to apply this logic to the wave function of the universe itself. Just as a particle can emerge on the other side of an energy barrier, a closed space-time geometry could tunnel through the barrier of non-existence. The probability may be minuscule, but in quantum mechanics, if it's not zero, it's not impossible. This model also aligns with the idea of a closed universe, a finite but unbounded space, topologically like a 4D sphere. In this geometry, the total energy of the universe could be exactly zero, the positive energy of matter balanced by the negative energy of gravity. From this perspective, the birth of a universe costs nothing. Critics point out that this nothing is still defined by laws, by a quantum field, by mathematical structure, by the very rules of tunneling. So is it truly nothing, or something deeper, a metaphysical substrate, a platonic space of possibility? We don't know. But this theory remains one of the most mathematically consistent answers to a timeless question. Why is there something rather than nothing? In Vilenkin's universe, the cosmos did not erupt into space. It became space, not in time, but as time. A sudden shift from absolute stillness to motion, heat, and the inexorable march of cosmic history. Perhaps the question is not what happened before our Big Bang, but rather which Big Bang. In recent decades, cosmology has taken a bold leap from a single universe to an ensemble of universes, a multiverse. Not science fiction, but the mathematical implication of eternal inflation. According to inflation theory, the early universe underwent a brief but extraordinary expansion, a trillion-fold increase in volume in a fraction of a second. In most models, this inflation doesn't end everywhere at once. Instead, it continues in pockets of space-time, endlessly bubbling outward. Each pocket becomes a universe, each with its own physics, its own constants, its own cosmic history. This process, eternal inflation, produces not one universe, but an infinite multiverse. Our universe is just one bubble in this cosmic sea. What lies beyond the edge of our observable cosmos may be another universe, separated not by space, but by inflationary history. Each universe may operate under different physical laws, different particle masses, different numbers of dimensions, even different space-time geometries. This diversity is not just theoretical. It emerges naturally from the landscape of string theory, a vast configuration space of possible vacuum states, each defining a unique universe. It is said there may be 10 to the power of 1,000 or more such configurations. This raises a profound and controversial question. Why does our universe appear so finely tuned for life? Why is the strength of gravity just right to form stars? Why do atoms exist? Why is the cosmic microwave background so uniform? Some physicists invoke the anthropic principle, we observe this universe, because only this kind of universe permits observers. In a vast multiverse of possibilities, most universes are sterile, chaotic, empty, or short-lived. But a few, by chance alone, support the emergence of complexity, of chemistry, of consciousness. But the multiverse raises an unsettling truth. If other universes exist beyond causal contact, can we ever prove it? Science thrives on falsifiability, on predictions that can be tested. And so far, the multiverse lies just beyond the reach of our instruments. Some hope for indirect clues, imprints of cosmic collisions, anomalies in the CMB, or quantum entanglements stretching across aeons. Others argue it may remain forever philosophical, a mathematical reality, forever just out of reach. We have traveled across cosmic epochs, through theories and time, past quantum foams and multidimensional brains. And now we must ask, what does it even mean to ask what came before the Big Bang? In physics, time is not absolute. It is a dimension linked to space, dependent on matter, shaped by energy. In the early universe, time may have been emergent, not ticking, but arising from entropy, information, and quantum states. The Big Bang is not the origin of things in time. It may be the origin of time itself. And if time began at the Big Bang, then before may be as meaningless as north of the North Pole. Still, the human mind resists silence. We want origins. We need reasons. We yearn for first causes. So we ask, Did the universe emerge from quantum fluctuation, from a previous cosmic cycle, or from something we have no language to describe? We do not yet know, and perhaps we never will. But what we can say is this: the Big Bang is not the end of the story of time, it is the beginning of questions. Questions that force us to stretch the limits of thought and language, to rethink what it means to exist, to challenge what it means to begin. Science does not shrink in the face of the unknown. It leans into it with equations, telescopes, experiments, and imagination. And as we peer closer at the origin of time, we glimpse something more powerful than answers: wonder. Thank you for joining us on this journey. If the universe has a beginning, may our curiosity never find one. This is Anantum and beyond. And this is just the beginning.